So I just wanted to take a few minutes to look at the force between charged objects. This is called Coulomb's law, but we're going to get there step by step. The first logical thing to do is to just say, well, imagine that I've got some charge Q1 at this location, and somewhere else in the vicinity I'm going to have a second charge, Q2. And in between the two charges is going to be some distance, and we can just call that distance r, or little r. Okay, so their distance r away from one another, and we could say that, well, they have to be exerting some sort of force. We know that if they're both positive, then they will repel on one another. So let's just go with that convention and imagine, well, if they're positive, a little positive in front of each of these, we could say that, well, there's going to be a force by 1 on 2, and there's going to be a force of 2 on 1. So the larger, well, we could say, okay, we'll just draw these out. So we know that there's going to be a force of 1 on 2, and we also know that there's going to be a force of 2 on 1. Okay, and so these are magnitude and direction, so just to be really clear, we're going to put an arrow on them, denoting that those forces are vectors. Okay, so back to the charges and this force that they're going to experience on one another. Well, let's just take, we know that they're going to be equal magnitude. They're a Newton's third law. They're a force pair. So the force is going to be proportional to whether it's either of the forces. And well, how much charge is there? So the bigger that the first charge is, the larger the force there's going to be. And then Q2 as well. And so the larger these forces, the larger these charges, the larger the force. So that makes sense. And then we can do an experiment where we look at measuring the amount of force that these charges are exerting on one another. And what we find is, as they get farther away, the force rapidly diminishes as 1 over r squared. Okay, so we know that with more charge we get more force, and as we separate them we get less force. In order to make this into an equation that we can pin exact numbers on in the units that we commonly use, we could do an experiment and we could measure what sort of proportionality constant gives us an equal sign. And we can measure a value for what we'll call K, or Coulomb's constant. And so here, now we've got an equation that describes the electric force between two charged objects at a certain distance away. And if we look at the units, that we're going to have for charge, we call coulombs. Okay, so for example, the fundamental charge, E, which is the small basic charge, 1.6 times 10 to the negative 19 coulombs. Now, because that's a really small number, and we often are going to use microcoulombs, just because that puts things in kind of reasonable numbers. Now, units in terms of this constant, well, we've got standard units for force and for distance, and we can define this one for coulombs, for charge. But then, well, what units do we need in that constant value? Well, we know that force, the units are going to be kilogram, because we know force is equal to MA, so the units of mass are kilogram times A for meters per second squared, right? So that's on the force side. And the units have to be equivalent on the other side. So we know we've got, well, we don't know what the units of our constant are, K, but we could say, well, this is coulombs and this is coulombs again. So we've got two charges. And then over some sort of distance. So we could say, over squared meters. So in order for this all to make sense, the units for K have to be newtons times meters squared per coulomb squared. Okay, so newtons are the other way that we can write our units for force. And so if we do that, right, if we write all this in, then this side of the equation here will end up being newtons meters squared per coulomb squared times our existing units. And that's going to be equal to, well, C's cancel, the meters cancel, and so what we're left with is indeed newtons. Okay, so for our K value, we actually can calculate through experiment a value of about 9 times 10 to the 9. That's a kind of rough value. Newtons meters squared per coulomb squared. Okay, and this is Coulomb's constant. Now this constant is actually constructed from something that is arguably more fundamental, which is the permittivity constant, or vacuum permittivity, which is denoted with epsilon naught. So we can also write this equation, Coulomb's law. So we'll just kind of label this. I'll do it in a different color. So this is Coulomb's law. Okay, so we can also write this with K, which is related to epsilon naught, which is equal to 1 over 4 pi epsilon naught. So sometimes also see this equation where instead of K, it's 1 over 4 pi epsilon naught, and then Q1, Q2 over R squared. And that's fine too. In some ways that's more rigorous. However, for a lot of our uses in this course, it would be fine to use K or Coulomb's constant. But you should know both and be able to relate them from one to the other. And you can look it up, but epsilon naught here has a value of about 8.85 times 10 to the negative 12. This was very, very small farads per meter. Okay, so that's a really, really small number. So in any case, this is Coulomb's law. Now, notice how similar in structure it is with gravity. right, if you recall, our equation for gravity, the force caused by gravity, is surprisingly similar. So in that case, we had Fg is equal to, well, it depended on the two masses. So we could say, big M, little m. And it was also 1 over distance squared, or 1 over r squared law. And then there was a proportionality, there was a constant called g. So that's our force of gravity equation. And, our force, our Coulomb's law, or the electric force, is Q1, Q2. But you know what? Just to make it look more similar, I'm going to say big Q, little q, that's fair, over r squared. So they take exactly the same structure. And that's very interesting. You could also then consider, well, how do they compare with one another? They look very similar. They're both very important to nature, to understand how the universe works. But there's a stark difference between these two. Now let's try an example where we look at the force due to gravity and that of the electric force. So you could have, consider two protons. We'll have some object there, positive, and then some object here. So you got two protons, identical mass, identical charge, same charge, so repulsive force, and they're going to be some distance away from one another. Okay, well, we can call it R, or we could call it D, whatever. So consider these two are going to interact using both forces. So in the force of gravity, we're going to have a really, okay, so first we'll go with G. So our value for G is 6.67 times 10 to the negative 11. And that's newtons meters squared kilograms squared. Okay, and then we're going to have a very, very small mass for the protons. And that's going to be 1.67 times 10 to the negative 27 kilogram. And there's two of them, and they're identically massed, so there's squared. All over some distance we're going to call r. Oops. Okay. So we don't know r, right? But let's just consider a more general case. Now that's, I'm actually going to put this a little bit lower down. Okay, so let's now consider the electric force. It also has a proportionality constant, and that'll be about 1.6 times, that'll be 9 times 10 to the 9 Newton meters squared per Coulomb squared. So that's our K value, and then we're going to have two positive charges. They're protons, so they've got the fundamental charge of E, and the value for that is 1.6 times 10 to the negative 19. And there's two of them again, so this is squared. And this again is all over the distance, r squared. Okay, so that's looking very similar. So in fact, we can do this in a more general sense, and we can actually divide these two equations. We can divide them. And what that's going to do is when we divide them, we end up with a relationship between the two. We actually could have done this for basically any two interacting. Okay, so the ratio between the electric force and the force of gravity is going to end up being around 10 to the 36. That's a huge number. What does that mean? Well, it means something very important for the way everything works, that the electric force is around 10 to the 36 times as powerful as the force of gravity. That's enormous. And it actually makes sense with your observations. If you imagine taking a balloon and rubbing it in your hair and developing a static charge on that balloon, well, then you can pick things up. Light things, admittedly, but things nonetheless. Pieces of paper, leaves, stuff. Paper clips, maybe. And that means that that small amount of charge that you took off your hair, added to the balloon, was able to overcome the downward pull of the entire planet Earth, exerting a gravitational force on that small object. So all the time we see the impact of the electric force being much, much, much stronger than the gravitational force. In fact, the gravitational force is so weak, it's a point of investigation in theoretical physics. To answer the question, why is gravity so weak compared to the other fundamental forces? Okay, so that's something to consider for just how important and strong the electric force is. That's it for now.